Hi, this is Jeff Heaton. Welcome to Applications of Deep Neural Networks with Washington University. This is Module 7, Computer Vision, Part 2, Convolution Neural Networks. Convolutional Neural Networks. Okay, this is the information from your module. This diagram that you see of convolution neural networks is a very common diagram. It comes from Jan LeCun's original LeNet 5, which is sort of the seminal paper for a lot of this stuff. Some of the terminology is a little different, but the idea is all basically the same. You have the input, which is 32 by 32. You have the convolutions, which is as the square essentially scans across the input. And the weights are the same no matter what part of where it's scanning. That way it can detect an edge of that A down here or up here, and it's all the same edge if it happens to be present. Or if one of the convolution filters is designed to detect an eye, if it finds an eye here and then an eye here, those are both detected potentially with the same weights. And it builds these feature maps. These feature maps are typically called the convolution layers. And the subsampling, those are typically called maxpool or pooling layers. These are all introduced in this class. There's no dropout layer up here because that hadn't been invented yet, but dropout layers are often used in conjunction with this. We will definitely see dropout layers in a upcoming module very soon. So let's look at the convolution layers first. The convolution layers are essentially, they're typically called filters, so number of filters. You can think of the number of filters as how many hidden neurons the layer essentially has, because the more filters you give it, the more different patterns that it can start to recognize. And then the filter size. So this is sort of a 4x4 one. Usually they're squared. Depends on the implementation. Stride determines how quickly it's moving across. So if the stride is 1, it goes 1 pixel, 1 pixel, 1 pixel, gets to the end, and then goes down, and then 1 pixel, 1 pixel. Usually the stride will be 2 or something larger so that it's kind of bumping across as it goes through. Padding deals with the edge. So you can pad it with a bunch of zeros completely around it. And often you will use padding. So I am using padding there, you can see, because there are definitely a lot of zeros. And then the activation is typically ReLU, rectified linear unit. These are all of the hyperparameters that you specify when you are going to create a convolution layer. In TensorFlow are really in just about any of the other packages that support them. We will, in this part, we'll look at the sort of graphical, constantly updating ConvNet.js, and then we will look at how to actually implement that. That'll be part 2, which we're in, and then we'll look at how to actually implement them in part 3. So this filter, as it's being drug across, would have a number of weights that would learn to recognize individual patterns. So that would let it recognize it potentially at the top or potentially at the bottom. So maxpooling layers are another technique for this, another layer type. These are essentially downsampling. They take something of high resolution and take it down to a lower a lower one. So here is, this would be doing a 2x2. So we're taking 2x2 sort of sizes and shrinking it down to this. So if we divide this all into 2x2x2 and this to 2x2x2, we get a total of 9 divisions, and this shrinks down to 9. So that's the pattern. You take the max in each of these. So the first box here, the max of 1, 7, 4, 8 is 8. So 8. Max of 122 is 2. Max of 1326 is 6. So that is max pooling. It is basically shrinking down the amount of data that the neural network has to actually look at as it flows through these various layers. This does lose information, and max pooling layers are somewhat controversial. Geoffrey Hinton does not particularly like them and has described them as various things such as a bad direction in computer vision, and there was an entire discussion with Hinton participating on Reddit about these. So let me show you some information from the Convolution Neural Network class in computer vision. They've got a couple of animations that I find really useful. This is by the same person who wrote the JavaScript example that we were looking at earlier, and we'll look at it in greater detail now. So this is showing you a convolution literally happening in real time. So it's similar to my diagram, except it's way cooler than my diagram because it's animated. I believe this is JavaScript doing this, or it's one big giant animated GIF. But anyway, what it is doing is, here is the input data. Notice how there's 3 parts. That's red, green, and blue. And it is scanning over those, and you'll notice that the stride is 2 because it jumps 2 each time. The filter that we have here, there's 2 filters, W0 and W1. So these are 2 filters that we specified in the convolution stack. And each of these is potentially learning different patterns because they each have their own weight. Now notice you have to do weight 0 first and then weight 1. They're not at all connected. They're simply, it's like 2 neurons in the hidden layer. Each one is operating largely independent of each other. And then the output from this becomes 3 by 3. So the filter size, which was 3 by 3, by 2. Notice we don't have the RGB depth anymore. The depth now is the number of filters. So this is showing you basically how it's calculating these all with real numbers and doing the scan, just like a real convolution network actually does. And then he's got some implementation notes on how to actually create that. Now, if you remember from part 1, or if you watched part 1, we had started using ConvNet.js, which is, and I've got links to all of that back in the module information, but we had started using ConvNet.js and we were running it, and it was slowly training as we, and this is by Andrei Karpathy, the same individual who did the class for Stanford. But you notice now it is getting quite a bit better. Well, at least somewhat. The ones that are better are the ones with green near the top. So it's classifying that as a truck. It's thinking that car is a frog for some reason, so that's bad. But this is a very quick and dirty sort of implementation of this running 100% in JavaScript. No GPUs, nothing fancy. It's running literally in your browser. It's really pretty impressive that he was able to get that working in JavaScript so well. So let me show you up here sort of the structure, because the structure of all of these is really pretty similar. Whether you're dealing with TensorFlow or Keras or really any of these, this is ConvNet.js. So this is written in JavaScript, but it's pretty similar to what you'd see in Python. So here he's setting up the layers. This is kind of like in Python when we were building the sequence and just adding to it. So this is the input layer. And the input is 32 by 32. So it's taking those 32 by 32 CFAR images, depth 3, because they are RGB. And the first thing that they're being fed into is a convolution layer, which is here. Here you have the hyperparameters, which are similar but not exactly the same as, they're different names, but they're accomplishing the same thing. So here you're specifying the size x. You're not specifying y because they're all assumed to be square, so y would be the same. This is the number of filters. So we have 16 convolution filters. Stride is 1, pad is 2. So you're padding it with two sets of zeros completely around. The activation function, just like we've been using through much of this semester, is the rectified linear unit. So you define a convolution, then a pool, then a convolution, then a pool, convolution pool, and then finally you softmax it, just like TensorFlow. So there's 10 classes, or curas I should say, and those are your final 10 input neurons, and you construct it. Now, what's pretty cool is JavaScript is so dynamic, he lets you literally just change the network here. So you could try this on a bigger or smaller network and experiment with it and see really what that might look like. But this is the input layer here, 32 by 32 by 3, so the RGB. It's showing you the input and the gradients. The gradients are a little bit harder to read. That's part of the training. But the area that has the most color is where the weights are being changed really the most, if I understand how he's representing that on there. So you've got the active gradients here. So where you've got the color, that is where it's actually changing them. So this is the convolution. He had specified 16 filters, so those are them there. And the activations as those filters are being trained. And then you can see the weighted gradients and the weights. The interesting thing on the weighted gradients is you can see definite color specialization on that. And you can see the different patterns that it's sort of trying to learn on these. And he shows the rectified linear unit. So the rectified linear unit, once it hits this, that's sort of the end of the color information because it's maximizing. And then the pooling, it's taking it now down to the smaller size. So we're losing our resolution on the pooling. We've already lost the color. And this is because the color really inputted more up here and is now encoded into the very bits of these images. Then another convolution, more weights. And finally, at the very, very end, the last rectified linear and pool, he basically passes it through to the softmax, and now we're classifying. So whichever has the darkest color, or probably the lightest, probably the white, so that's the one that it's actually classifying. And it's softmaxing it, so these should sum to 0. I'm sorry, to 1. So these are all your layer types. You've got pools, you've got softmax. It's all very similar to the other types of neural network, except that you have the pooling and convolution layers. And this shows you visually what's going on inside of it. Even seeing this visually, it's still very hard to explain exactly what's going on in the neural network's mind. You can see it finding edges, you can see it finding shapes, you can see what parts it's training on primarily, but it still can be very difficult to truly understand what's going on in the neural network's mind. And these are fairly small networks. We'll see there's something called the ResNet, which just literally adds hundreds of these layers for computer vision. All right, that is the end of this part. We've seen how to make use of or at least the concepts behind these different layer types. In the next part, we're going to see how to actually implement that in Keras.